Hi everyone. This is the lab for April 1st, both Physics 112 and 102. Let me bring up our lab. Just to be clear, we are, I did explain this in the email, but we were actually scheduled on April 1st to do the thermodynamics lab, but it's just not at all something that can be done well online. Even in the lab, it would have been a very short lab, and there's just very little for me to give you through this kind of virtual environment. So I'm going to skip it. So what I'm going to do is we're actually going to go on to electricity, which is going to be our first topic right after the second test. So we're getting a little bit ahead of the game, but that's okay. There's a lot of stuff to be done with electricity. Probably what I'll do is I'll expand either the electricity labs, or expand the one of the optics labs, or I'll create some other lab in there. This actually gives me even more freedom to do something which is much more appropriate for a kind of a virtualized environment. These labs were never meant to be taught this way, and so it just caught us unaware. If I'd even had like a week in there, an extra week where I could have gone into the college. We literally are not allowed into the college. I could have probably videotaped them all, just done them and videotaped them, and then we would have been better off. But under these conditions, it's just not at all something that I can do. So anyhow, let me see how many people are watching. 13 people are watching. Okay, so just remember there's a 30-second delay. Whoops, I lost the window again. There's a 30-second delay, and um, I'll look at the chat every once in a while and see if you have any questions, and then go back over it. Okay, so we're going to do today the electricity lab number 1. Okay, and it's right here. All right, and um, I'm going to introduce some concepts from electricity that we'll actually get to probably not next week, but the week after that. We'll probably have covered everything that you're going to see in this lab. So we are getting a little bit ahead of it, but it's okay because these concepts are not that difficult. All right. So the lab is entitled Introduction to Electronics, and basically there's two instruments that you would use in this lab to do measurements. One of them is the oscilloscope, and we saw the oscilloscope uh, last class. So I'm not going to ask you to re-go over those videos about the oscilloscope. You can give some brief description of how the oscilloscope would have been used in this lab. But there is a new instrument that is going to be introduced, and it's a multimeter. And a multimeter is very, very useful. In fact, it's so useful that practically every household can have a multimeter in it. And so I'll tell you what kinds of things you can measure in the multimeter. And I've got a few YouTube videos that describe how multimeters work. And they're used everywhere, like, car garage, when they're fixing cars, they'll use them. Around the house, if you want to check for, electricity in any of the sockets, it could be used there. For electronics, to see if a fuse is blown. So extremely useful devices. I've got a few myself, actually. Okay, so those are the instruments in this lab, and the actual physical components that you would have played with and plugged in would have been resistors. Mostly this lab is about resistors, okay? But there's also like wires and switches and so on, all right? But resistors, and what we're going to study with resistors is this Ohm's law, looking at them in parallel, in series, and in power dissipation. So actually, if you towards the end of the lab, I'll actually point out my short little summary of what I expect to see in your lab write-up. I'll discuss these three things because these are kind of the 3 points that this lab is about. Okay, it's demonstrating Ohm's law, what happens when you have resistors in series and parallel, and power dissipation in resistors. Okay, so at this point you're like, well, I don't know what a resistor is. I don't know any of this because you haven't been introduced to electricity. That's right. So let me give you a very quick introduction into electricity, and not a general theory of electricity, but just electricity in circuits. Okay, and this is very useful because not only is your house a circuit, but also if you want to describe things, like if you're in biology, you want to describe say a muscle, how muscles work and how nerves work. Those are all electrical circuits at the microscopic level. Okay, so the kinds of things that we learn with circuits and playing with like resistors and switches and so on in the lab actually have very close analogies in, I don't know, so many different places it's hard to think of them. But like even in the human body, okay, there things act like resistors and things act like capacitors, which will be the subject of next week's lecture. Next week's lab, and even in the lecture and so on. So yeah, this stuff is quite universal. All right, so what's our quick theory of electricity? Okay, so let's scroll down to. This just describes the components. There should be theory down here. There we go. Theory of electrical circuit behavior. Okay, and let's look at this right here. Okay, that equation right there. V is equal to IR. That's called Ohm's law. And you're wondering, what is V, what is I, and what is R? And let's take a look at this circuit here. Okay, so let's go through each of them. So, well, there it is actually rewritten. It's rewritten there as I is equal to V over I, but that is called Ohm's law. What are the three quantities in Ohm's law? So there's this thing called voltage, and you've heard voltage all over the place, okay? You know that your house works at 110 volts. You know that when you buy batteries, they're like 9-volt batteries. There's 1.5-volt batteries in different sizes and so on. So what is this thing called voltage, okay? Well, voltage is a kind of a push. There's a certain amount of a push that batteries or power supplies give to the electrons in a circuit. Okay, the electrons, like they move around, but they don't have any preference to move one way over another way. They'll just kind of like bounce around randomly. But if they feel some kind of a voltage, that'll push them in some direction. Okay, and so that's exactly what a battery is. A battery is a push. And actually, if you want to bring that back to the physics that we've done up to this point in the course, this push is actually so many joules for every electron. Okay, or actually per coulomb, but you don't know what a coulomb is yet. Not that that's important for this lab, but this is just so much push for every single electron. Every single electron gets a little bit of a push, and that measure of how much energy is given to each electron to force it around the circuit. This is known as the voltage. So you could just think of it as a kind of a push. All right. So great. In this circuit diagram that you see here, this symbol right here, the alternating short and long lines, this is a battery, a power supply. And so there is the long line here, that's like the positive, and then the short line is like the negative. Okay. Let me see if there's any, no questions in the chat. Okay. Whoops. Oh, darn. It seems that, there we go. All right, so there we go. This is the positive, and that's the negative. Now the negative, that's where the electrons are. They're getting this push, and they're being pushed through this wire here, and they would be pushed. Never mind this jiggly line here. That's a resistor. They would be pushed, and they would be pushed, and they would be pushed, and they would get to the other side. Okay. Now, because they're being pushed, it's not just one electron that's being pushed. There's a whole bunch of them that are being pushed. Okay, and so as they flow from one side to the other, you can ask a very simple question. How many flow per second? So how many electrons are being pushed around this circuit per second? All right. And that's the current. All right. And the current is just like the current in a river. You can have a river which is got a lot of water in it, but it moves very slowly. That would be a low current. Okay, or you can have a river which has a little bit of water, but it's moving fast. That's still low current because it's not a lot of water moving, even though it's moving fast. But if you have a big river with a lot of water flowing, okay, or in the electrical equivalent of it, you have a lot of electrons being pushed around here very fast. You got a big flow through there. That's a big current. Okay, that's your I. All right, and finally, what limits how much that current is going to flow? That's your resistor. Okay, so it's pretty obvious how this works. The bigger the resistor, the more it's going to limit the flow for a given battery. In fact, you see that in the formula here. The bigger R is going to be, if you make a bigger R, you're going to get a smaller I. So the bigger the resistor, the less current you're going to get. Makes sense. Okay. Conversely, the bigger the push, the more that oomph that the battery gives, the more the energy that the battery gives is going to be able to overcome the resistance, and the more it's going to flow. Okay, so the bigger the voltage, the more current you're going to get. Okay, and Ohm, who was a physicist, did a lot of experiments measuring how much current would travel through different materials for a given voltage. Discovered this law, and discovered resistance, and it's known as Ohm's law. Okay, so it's written this way, or equivalently, you can see it written like that. Okay, there it is right there. V is equal to IR. Now, just one more thing about the units here. Well, we really haven't studied this formally. When I do this formally, you'll see all the units being properly worked out. But basically, voltage is measured in volts. Okay, so that's easy. That's something you're familiar with. It's going to be a measurement of energy per unit charge. All right, but you don't need that for this lab. But that's voltage. Okay, current is actually in amps. Okay, and amps is so much current, so much charge per unit time, so many electrons per unit time. Okay, and that's basically current, and it's measured in amps, named after Ampere, a French physicist. Okay, and resistance is in ohms, and named after Ohm. And so basically the way this works is that if you take volts and you divide it by ohms, you get amps. Okay, well, there it is. So this is the theory so far. Okay, so we'll do this more formally, but basically one of the things we want to show in this lab is that Ohm's law is true. All right, now if we were in the lab, what we would do is we would hook up different power supplies, we would hook up different resistors, and we would actually measure V, we would measure I, There are instruments for doing that. That's what your multimeter is. Your multimeter is the device which is capable of measuring V and measuring I. Okay, and we measure V, we measure I, and you can measure R, or you can get the rating right off of them because the resistors have written on them how much the resistance is. And what you do is you just plug in and say, well, did it work? Okay, because if you take the voltage and divide it by R, that should equal that's going to give you a number. Does that equal the current that was actually measured? Okay, and if the answer is yes, within some experimental error, then yeah, you've verified Ohm's law. Okay, so that's one of the things that you want to show in this lab. So how would you actually do this? I don't know if he's got a diagram here. I don't think so, actually. All right. Nope, there's no diagram. That's okay. I'll just describe it. Um, where was my diagram? There it is. Okay, I thought he might have had a diagram. Nonetheless, one of the YouTube videos that I'm going to have you look at, they will show you how you actually measure the current and the voltage using a multimeter. Okay, so what can a multimeter measure? One of the things it can measure is voltage. And the way you measure voltage is you put a multimeter probe on one side. Well, if we were going to do the voltage across the resistor, you put like one probe over here and you put the other probe on the other side. It's basically got these two probes, and you just put a probe there and a probe there. And you set the multimeter to measure voltage because it can measure many different things, and it'll give you the voltage reading. Okay, so basically you just touch a probe there and there. For the current, you actually have to cut the circuit and put the multimeter inside the circuit. So you force the current through the multimeter. Okay, and then it, set the multimeter to measure the current, and it'll measure the current. Okay, and then there's yet another setting where you can actually disconnect the resistor, and it'll actually measure the resistance. Okay, so you can measure all three things on the multimeter, V, R, and I, and again, does it work? Okay, just the technique for measuring each of those things is different. But like I said, on my video that the YouTube video that I found that shows how to use a multimeter will actually show you how to measure all three quantities. Okay, so where are we at here? At this point, we've basically looked at the theory behind A here, Ohm's law. Okay, so that's one of the purposes of your lab. All right, so when you write your introduction, you're going to say, what am I doing? What's the point of this lab? One of the points of the lab is to prove Ohm's law. Okay, and the next point of the lab is to show how resistors work in series and parallel. Okay, so what's that about? All right, well, you kind of saw series and parallel when you did the spring lab. Remember Hooke's law, where you hooked up the springs one after another, one after another? That was in series, and then you also hooked them up side by side. That was in parallel. Well, you can do the same thing with resistors like that. Whoops, went a bit too far. There you go. So let me make my image smaller. There you go. Now you can see them all. Okay, so here are two circuits. And in the circuit on the left there, it says resistors in series. Basically, you put one resistor after another. Okay, and in this case, the current is forced to go through all three resistors. So just think, picture what it would be like from the point of view of the current. The current is forced to go through the first resistor, then it's forced again to go through the second resistor, and then it's forced yet again to go through the third resistor. So it has no choice to go through all three resistors, and guess what? It feels the resistance of all three resistors. Okay, so whenever you hook up resistors in series like that, the resistance adds. Okay, so here we have four resistors that are all of the same size. They could have been in different sizes, it doesn't matter, but basically it's going to be this resistance plus that resistance plus that resistance, and that's going to be the total resistance. Okay, so just to give you an example of something which is outside of like just pure electronics, in human tissue, you might have like one layer of tissue, then you have another layer of tissue, and then you have a third layer of tissue. And if some kind of current has to travel between all three layers of tissue, well, then the resistance that current would feel is the resistance of the first tissue plus the resistance of the second tissue plus the resistance of the third tissue. Okay. Conversely, you can hook up your resistors in parallel. And now you can imagine what the current experiences. The current comes through here and it gets to that point right there. And when it gets to that point right there, it says, oh, look at that. I've got a choice. I can either go that way, or that way. So the current actually splits in three ways. And so only a third of the current feels that resistor, a third of the current feels that resistor, and a third of the current feels that resistor. The effective resistance of all three of these is actually less than any one of them, okay? Because you've allowed less, because you've forced less current to flow through each resistor, you've effectively decreased the resistance, okay? So whereas here the resistances add. Here they don't add exactly. What do they do? Like, how do you combine these three into one resistance? And the answer is, so here in this diagram, Dr. D is showing that, in series, the three resistors add. Okay, so you get R1 plus R2 plus R3 gives you the effective resistance. Okay, but what happens if they're in parallel? Well, in parallel, the formula is rather different, and there it is at the bottom there. So it's actually not the resistances that add, but the reciprocal of the resistances that add. Now, the theory for that we'll do in class. Okay, so right now we're just trying to verify this, and so we'll ideally you would have hooked up this circuit and you would have measured this to see if it's true. But basically you have like this is one resistor, there's another one, there's another one. You don't add 4.4 plus 4.4 plus 4.4. You add 1 over 4.4 plus 1 over 4.4 plus 1 over 4.4, which is this part here, okay? And then the result is the reciprocal of the answer. Okay, and so it's like the reciprocal of the sum of the reciprocals, all right? And if you work that out, for this particular situation, you only get 1,467 ohms. Well, we got to be a little bit careful here. And I was going to mention this later, but now maybe is a good time. Resistance, 1 ohm is really, really small. Okay, an ohm is really, really small. So usually resistors are in kilo ohms, but the MKS unit is 1 ohm. Okay, so here we have 4.4 kilo ohms, 4.4 kilo ohms, 4.4 kilo ohms. That's 1,467 ohms, or 1.467 kilo ohms. Okay, so 4 plus 4, 4.4 plus 4.4 plus 4.4 in parallel actually wind up only being 1.467 ohms, kilo ohms, sorry. So it actually decreases, and that's again because the current is allowed to split. Let me look in the chat to see if there are any questions so far. And oh, no one's how many people are 14 people watching, and there's no questions. Okay, and so great. There it is. So what would you do? What are you expected to do experimentally? So the theory is, like I said, something that we'll go over in class, probably in a week and a half time. Doesn't take that long before we get to resistance, and I'll actually prove this from deeper principles. That it works that way. But in the lab, what you would do is you would basically hook up a circuit like this. Okay. And what you could do is you could either, hook it up to a 10-volt battery and, measure the current, measure the voltage, and then use Ohm's law. Or, with a multimeter, there's actually a resistance setting on it. So you don't even need the battery in there or anything like that. You just put the three resistors in series like that, and then you put one probe right here at the one end of the multimeter. You see, you put a probe there, and then you have resistor, 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 and then you put the probe at the other end, and you set the multimeter to measure resistance, and it'll tell you the resistance. Okay, what do you expect when they're three in series? You would expect the multimeter to say 13.2 kilo ohms. Does it? Well, it does. Okay, I mean, this theory is pretty well established, so it would. Okay, so and here in the lab write up, he's got three resistors that are the same, but in the actual lab you would have done several different resistors, and for all of them you would have found that if you just add the resistances, you get the effective resistance when they're in series. Okay, similarly, you would have hooked up three resistors in parallel like that, and you would have then just measured the resistance across there. Again, you don't even need the battery. You would just put like a probe of the multimeter there, and then put another probe there, set it to measure resistance, and you would find that it actually measures 1.467 kilo ohms, or 1,467 ohms. Okay, and so what does that prove? That proves how the theory behind how resistors combine to give you an effective resistance, depending on whether they're in series or they're in parallel. In the class, we'll actually do quite a few different configurations, we'll do both series and parallel and so on. But in the lab here, it's just sufficient to show, that how the series add and how the parallel add, pure series and pure parallel. Okay, so this is the second part of the lab, and I've got a video. I found a very nice video online that demonstrates this. Okay, and so let me see, any questions so far? All right, guys are kind of quiet. It's pretty straightforward lab. Okay, so then the last thing, if you go all the way to the top here, there is the third thing that you're supposed to show. Okay, and the third, I can't do highlighting here. Okay, the third thing is power dissipation in a resistor. Okay, and one of the things you discover that when you do this lab, okay, especially when you have the smaller resistors, when you go to touch them, you discover that it's pretty hot. The resistors are pretty hot. Okay, so what's happening in this circuit here, got to scroll all the way back down to the bottom. See, most of this is describing, the components that you would have used in the lab, but, I mean, we don't have a breadboard, so can't really, don't bother, I should even bother. There's no reason to bother talking about it, but let's go back to this diagram here. Okay, so, you have this circuit here. It's a very simple circuit, and the current is running through here, and this current is encountering this resistance in here. All right, and you have to think about it from the electron's point of view. What is this resistance? Well, those electrons, they really want to zip across here, but they hit this resistance in there, and what that is these electrons, they're basically colliding into the atoms. And when they collide into the atoms, I mean, they're going pretty fast, and then boink, and they hit the atom, and they give the energy up to the atom. Okay, now we just finished studying thermodynamics, and in thermodynamics, we know that the average kinetic energy of the particles is the temperature. So if these electrons are speeding up the particles in the atoms and the molecules that make up the resistor, okay, and they have greater kinetic energy. Well, if they have greater kinetic energy, they have more heat. Okay, and actually Joule himself discovered this. It's called Joule heating. So whenever you have a current traveling through a resistor here like that, it'll actually heat up the resistor. Okay, and one of the things we would do in the lab is, you would touch these resistors and you would see, yeah, they're pretty hot. Okay, there wasn't a really good quantitative way of measuring it, but you would qualitatively be able to see that, yeah, resistors that are dissipating more energy per unit time, which is power, or they're so resistors that are dissipating more power per unit time, more energy per unit time, they're hot. And resistors that are dissipating less energy per unit time, they're not quite as hot. Okay, so you could actually see that. But you know what? You guys know this from everyday experience, because a light bulb, like the old, not the LED light bulbs, but the old incandescent light bulbs with that tungsten filament in there. Okay, the reason they're giving off light is because that filament gets hot. It gets white hot. Okay, and that's basically because the tungsten has a lot of resistance in there, and that resistance, causes the energy flow, the energy from the current flow through there, to heat up the tungsten atoms, and they'll get hot enough that they'll actually start to glow. Very inefficient way of producing light. Okay, but nonetheless, it worked, and it was based off of Joule heating. All right, so there's a formula for that, and let me show it to you down here. There it is right there. Okay, and there's various forms of it, but probably the form which is most intuitive is this one right here. Okay, and so it's P is equal to VI. Now, what is P? We actually saw power just very briefly when we did sound intensity. Power is measured in watts. Okay, and a watt is a joule per second. So you can have a certain bundle of energy. But if you keep delivering more and more bundles of energy over and over and over, then you're going to have so much energy being delivered per unit time. That's power. So, for instance, most microwave ovens are rated at 900 watts. What does that mean? That means that, if you put a cup of water in there and you turn on your microwave oven, it's going to deliver to that water 900 joules of energy to the water every second. So every second, the water has 900 joules of energy more, 900 joules of energy more, 900 joules of energy more. And so whenever energy is delivered over time, that is known as power. Okay, so there you go. That's the P, and it's measured in joules per second, or watts, named after Watt, another English physicist. And V is the voltage, and I is the current. And now you might say, well, wait a sec. Why is the power equal to the voltage times I? Okay, and the answer is basically because remember the voltage is that push. Okay, and so the more push there is, the more energy these electrons have, and so the harder they're going to hit the atoms, and so each collision in higher voltage is going to deliver more energy to the particles. Okay, so the bigger the voltage, the more energy is being delivered to the particles in the resistor, and of course the more power is going to be delivered. Okay, the hotter the resistor is going to get. But it's not just the 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 intensity of each collision. Okay, it's also how many collisions there are. So if you have a very low current, you're not going to have that many collisions. They might have a lot of oomph. Each collision might have a lot of energy, but there's not going to be a lot of them. Okay, so the more collisions there are per second, that's your current. The more collisions there are per second, the more energy is being delivered to the resistor. Okay, and so basically the resistor will dissipate the energy as heat. It'll just turn that electrical energy into heat. And if you take the voltage across the resistor and you take the current traveling through the resistor, okay, and you multiply the two together, you'll get the power. Okay, I'll do a better theory of that, better derivation of that in the class. But basically, this is the third point of the lab. And so in the lab, what you're going to do is, or what you would have done, is you would set up these resistors, and you would know the voltage across them, and you would know the current through them because you can actually use Ohm's law to carry the two, calculate them, or you could even use the multimeter to measure it, to measure V and to measure I, and you would have some resistors where V and I is small, and you would touch them, and they're not as hot as the ones that are, you know, have a big V and a big I, and they would be much hotter. Okay. In fact, this is how fuses work. So the last thing. So since we can't really, wouldn't have been able to really uh, uh, measure the amount of heat dissipated. What? Oh, there is a picture. There's a picture of how the multimeter is hooked up to measure amps. Okay. There is this last part here, blowing fuses. Okay, so this Joule heating, it's hard to, like, because you'd have to capture to measure it to actually see that P is equal to VI. You'd actually have to capture all that heat and measure it somehow. So it would be hard to do that. But you know what? That's exactly what causes fuses to blow. Okay, so what a fuse is, like in a car, or the older fuse boxes use these fuses. And if you looked inside of them, they had a little filament in there. Okay, that little filament, like a little tungsten filament, actually had a resistance associated with them. You could see it here as 33 ohms, pretty small resistance. Okay, and as the current would go through it, this filament would heat up. Now, the more current would go through it, the hotter the filament would heat up, until they get to a point where the filament would actually break. Okay, would melt. All right, and that's what we mean by blowing a fuse. Okay, so these fuses, when they would get hot enough, when P would get big enough, then they would melt, and then they would cut off the circuit. Okay, that's how a fuse works. So we actually had some fuses in the lab, and what we would do is we would they were rated at 33 ohms each, which is very, very small resistance. Okay, and you would put so much voltage on them, and you would get so much current, and then you would keep increasing the voltage, increasing the current, and then at some point it would just stop working. That's the point at which the fuse is blown. Okay, and if you multiply together the current times the voltage, that's the maximum power that this fuse would allow. Okay, now why is that a good thing? Why do you want fuses in your house? Well, if you're delivering too much power, or you're drawing too much power out of a circuit in the house, you're heating up not only the fuse, you're also heating up the wires themselves, because the wires themselves have a certain amount of resistance in them, and they would get hot enough to prevent a fire from happening in the house. And that's again Joule heating, because it'd be V times I. To prevent that fire from happening, you want to limit how much power you would allow through these wires. So the filament in the fuse only allows a little bit of power, and of course the wires in the house, they allow a lot of power through. So the fuse would blow way before, it would melt way before there would ever be a possibility that the wires in the house would start to get hot. Okay, so there's the third part, and what we would basically do in that part is we would just blow some fuses. Okay, as a demonstration of this Joule heating. You know what? I couldn't even find a good video online for this. So this third part, is just something that you might discuss as a purpose in the lab, but really without any kind of without any kind of like demonstration of it. It's not that deep anyhow. You know Joule heating because you know that whenever you put electricity across something, it gets hot. Here's another example. Electric stoves. Okay, well, gas stove obviously burns gas to produce heat, but an electric stove has those elements on top. Okay, and you know how they get red hot when you turn up the heat on those electric stoves. That's just Joule heating. You're just putting so much current across this resistor, the resistor gets hotter and hotter and hotter until it starts to glow. Okay, or houses that are heated by electrical baseboard heaters, same thing. Okay, basically there's a coil in there, and you put a current through it, and that coil of wire has a certain resistance, and it gets hot. Hopefully it doesn't get so hot that it causes a fire. Okay, that's what a fuse is for, but still, there's Joule heating. Okay, let me check if there's any questions before I talk about um, how to do the write-up. All right, so 14 people are watching. All right, so well, this is what I would have told you in the lab. The only other thing I would have told you in the lab, if we were like physically together, is I would have gone through the section where it says simple circuits. Okay, circuit components, and I would have shown you how to read a resistor. So there's a resistor there. Okay, how to read it, and also how to hook them up into a circuit using this thing called a prototype board, or sometimes it's called a breadboard. I don't know why, but it's a prototype board, and they're kind of cool because you get to get to build like little circuits with this, and you got little switches, and you can turn on LEDs and turn them off. And I used to play with these things in high school. They were a lot of fun. I think I remember building a little radio actually with one of these. I didn't know what I was doing, but I just hooked it up. Just hooked up the wires the way they were supposed to be hooked up, and magically I was able to get a radio signal from it. So they're a lot of fun to play with. But again, I can't really show you how to use one of these because we're not physically together. Okay, but there's a picture of like how you would hook up a resistor on one of these boards. Okay, so let me now go back to our lab here, our Moodle site for the lab. If you go all the way to the bottom, you can see lab 5 we skipped because that was the week that all labs were canceled. Okay, and lab 6, this is the one we did last week. Okay, so that's the one you should be handing in today. All right, and then lab 7, that was the thermodynamics lab. We're skipping that for the reasons I stated. It was a very short lab, even in the lab, but it's just not something that you can do much with in this virtual environment. So here we go. This is lab 8, introduction to electronics, and I have 1 2 3 4 5. I've got 5 videos there. The first one is actually a very nice introduction to how a multimeter works. Okay, not a lot of detail. It just shows like how you can use it to measure. And there's generally 3 things you measure with multimeters. Number 1 is voltage. Number 2 is current, and number 3 is resistance. Okay, so multimeters can be set to measure any one of these. There is a voltmeter which does only voltage. There is an amp meter which does only amps, but nowadays everyone just uses multimeters. Okay, and they're like about $15, $20 at Radio Shack. Okay, and then I found some nice videos which were able to demonstrate how a power supply works. That's basically a battery. Okay, and voltmeter and an amp meter. Okay, so basically this is still part of the kind of like getting into the results. Like before you actually do an experiment, you got to know how each of the components work. And so that particular video shows how like basically a battery, it's not really a battery, it's a power supply because you plug it into a wall, but it generates like 12 volts or 15 volts output. Okay, and how you can measure that with a voltmeter and an ammeter, which is basically a multimeter, but a multimeter set to measure volts, or a multimeter set to measure amps. Okay, and then there's actually a video online which does a clear demonstration of Ohm's law. And insofar as possible during the results section, okay, don't just say, I watched the videos. Try to say what you saw in each of the videos and how they actually apply to the point of the lab. Okay, now, and for verifying Ohm's law, the guy does actually have some numbers there. Okay, so you might want to report some of those numbers to say, in the demonstration we saw this number and that number. And then there's another demonstration where they actually do the videos in series and in parallel. Okay, this is actually an experiment where they do videos where they do measure the resistance in series and in parallel. Okay. There is a video on Joule heating, but I got to tell you, it's just theory. There's no actual experiment that's done. But nonetheless, you may want to watch that because it does explain how Joule heating works. Okay, you got to watch it. It's part of actually a list, and I didn't realize this, but if you just let it go, it'll go into the second video and the third video. No, you don't. You just need to watch the one video. Okay, but if you just let it continue to play, it'll play into the second, third video in the playlist. So just be aware of that. There's a basically one video on Joule heating, and it kind of explains what I just did, what Joule heating is. And what I'd like you to do is watch that, and then have in your discussion something about Joule heating, even though you didn't see it in a lab. You might want to describe Joule heating that you might have found somewhere, like in your house, like in incandescent light bulbs or an electric stove. All right. Let me just go into the summary of the lab here. Okay, so kind of wrote up, this is just to remind you later what I expect to see in the lab. So in your introduction, you should discuss the purpose of the lab. Okay, like why are you doing this? And what's the scientific purpose of the lab? I mean, obviously all of these labs are for educational purpose, but just concentrate on what you're scientifically trying to show. What physics are you trying to demonstrate here? And there is three, as I mentioned earlier. One of the things you want to prove is that Ohm's law actually holds, that V is equal to IR for a resistor. Okay, so if you were in the lab, you would have actually hooked up a circuit, measured V, measured I, measured R. So you've actually got the numbers for all three of them. You're not solving. You would say, oh, I times R, that's actually equal to V. It works. Okay, so you're trying to prove the theory. And then the second thing that this lab is about is like, what effective resistance do you get when you hook up resistors in series or when you hook them up in parallel? All right. And then the third thing that you're supposed to show in the lab is that resistors will actually convert electrical energy into heat. And they convert it according to the formula P is equal to VI. All right. And even in the lab, you would have actually, verified this equation quantitatively, but you would have verified it qualitatively by just touching resistors and seeing which one's hot and which one's not. Okay, so there's the purpose, and in the experimental, what you need to do is just describe what a multimeter is. Okay, so how it works. So there's that video that describes how a multimeter works, and always try to tie that back. You got this multimeter description of how it works. Always try to tie that back to the things that you're trying to measure in here. Okay, so how is the multimeter going to be used? Like, some of you will actually write out, step by step, like what you would do. So, try to imagine, what you would use how would you use the multimeter to verify Ohm's law? How would you use the multimeter to verify, that how resistors in series and parallel add up? Okay, and how would you use the multimeter to verify P is equal to VI? Well, actually, you not quite, because multimeters don't measure heat, but still they do measure V and they do measure I. Okay, for the results section, as I said, watch those YouTube videos, which they're pretty good. They demonstrate all the things that I wanted to do, except for really number 3, not quite demonstrated. Okay, and just say in your report, what you saw in the demonstration as results. And then finally, for your discussion, I guess you're trying to conclude. Did you actually, did the demonstration actually prove or disprove Ohm's law? Like, can Ohm's law ever be broken? All right. Well, it turns out that there are some weird situations where Ohm's law may not hold, but not for the kinds of things we're looking at. Okay. So, okay, there you go. That's the lab report. Okay. So let me look in the chat if there are any questions. Okay, there are no questions, and 13 people are watching. And oops, I lost the capture. That happens when I switch windows. Okay, so I'll just wait a few more seconds, and if there are no questions, that's it. Okay, and you can always email me. Like quite a few people emailed me because this is so unusual for a lab, and you go, "What are you expecting here?" And if you're not sure what I expect for each of the sections, just go ahead and email me, and I'll give you some kind of indication. All right, so that's it, guys. If there are no questions, then I guess we're done. I'll just wait for the view numbers to decrease, and then I'll cut the lab. Okay. Bye bye.